If you look at the red and blue protons, they're both attached to this carbon. And if we see this double bond here, we have these different groups attached to this double bond. And since there's no rotation around the double bond, the red and the blue protons are locked into different environments. Therefore, they are not chemically equivalent. And since those protons are not equivalent, they can couple together. And since this is occurring on the same carbon, we call this geminal coupling. So geminal coupling here. So geminal referring to the fact that both protons are in the same carbon, and coupling can occur. So those protons are close enough where they can affect each other. So let's think about first the Nmr spectrum with no coupling. So we would expect one signal for the blue proton and one signal for the red proton. So here's the spectrum with no coupling. But we know that the red proton's magnetic moment can align either with the external magnetic field or against the external magnetic field. And that causes the signal for the blue proton to be split into two. So if I go down here, so we actually see a doublet for the signal for the blue proton. Same thing for the blue proton. The magnetic moment can be aligned either with the external magnetic field or against it, and that splits the signal for the red proton into a doublet. So two peaks for the signal for the red proton. I went into much more detail about this in the spin-spin splitting spin-spin coupling video. In this video, we're more concerned with the idea of the coupling constant. And the coupling constant refers to the distance between the peaks of a signal. So if you think about the distance between the two peaks of this signal, that is the coupling constant. And the coupling constant is the same for both of these signals because these protons are splitting each other. They are coupled together. The coupling constant is measured in hertz, so it turns out to be 1.4 hertz. And if it's 1.4 hertz for this one, it must be 1.4 hertz for this one because those protons are coupled together. The reason why we use hertz is because it's the same coupling constant no matter what NMR spectrometer you're using. So it doesn't matter what the operating frequency is, you're going to get the same coupling constant. All right, if we look at the actual NMR spectrum, so over here is a zoom in of the actual NMR spectrum. The signal for the red proton is right here, and the signal for the blue proton is over here. So when I looked at this, when I looked at the spectrum with interaction, right, the spectrum with coupling between the protons, we just assumed that the heights of these two peaks were the same. But if you look at the actual NMR spectrum, they're not quite the same, right? So this one right here is a little bit higher. And if you draw an arrow pointing towards the higher peak, right, that arrow points towards the signal of the proton that's causing the splitting. Right, so that arrow is pointing to the right, and that's where we find the signal for the red proton, which is causing the splitting of the blue proton. So the doublet points towards the proton with which it is coupled. And the same thing for this signal, right? So this peak's a little bit higher, so we draw an arrow pointing towards the higher peak. And so the doublet points toward the proton with which it is coupled. And so you get this situation where you get these doublets with like a roof over their head, right? So if you can imagine this roof over them like that. So sometimes you'll see this on an NMR spectrum, and if you think about that they're pointing towards the proton with which it is coupled, sometimes it can help you when you're trying to understand what's going on in your NMR spectrum. All right, let's look at another example for a coupling constant. So let's look at this molecule. And let's focus on the ethyl group. So over here, this carbon has two protons. We expect one signal for those protons. And then over here, this carbon has three protons. So we would expect another signal for these protons. Let's focus in on the protons in blue. All right, so how many neighboring protons do we have? Well, those protons in blue are attached to this carbon. The next door carbon is this one. So how many neighbors? 1, 2, 3. So 3 neighboring protons. So n is equal to 3. And using the n plus 1 rule, we expect n plus 1 peaks. So 3 plus 1 is equal to 4. So we would expect a signal with 4 peaks. So we would expect a quartet. So let me go ahead and draw that down here. So we would expect a quartet for that signal. So this is supposed to represent what you would see on an NMR spectrum. Next, let's do the protons in red here. So how many neighboring protons do they have? Well, they're all attached to this carbon, and the next door carbon is here, and we have 2 protons on the next door carbon. So we have 2 neighbors. So n is equal to 2. And so we expect 2 plus 1 peaks. So 3 peaks or a triplet. So let me see if I can draw in a triplet here. So this would be the signal for these protons. Since the red and the blue protons are splitting each other, the coupling constant is the same, right? So the distance between the peaks should be the same. So it turns out to be 7 hertz. So this distance should be 7 hertz, right? Same with this distance. So we just have to pretend like they're all equivalent here. And the same for this one. So coupling constant of 7 hertz. Right, same for this signal, right? So this distance should be 7 hertz, and also for this one. So hopefully this just gives you an insight into the idea of a coupling constant, which you'll need to understand more complex splitting, which we'll talk about in the next video.